Starship's first flight destroyed the concrete underneath the pad, throwing it across the surrounding landscape. In order to solve this, SpaceX has built a unique water deluge system unlike anything we've seen before. We're approaching Starship's second flight and we keep seeing your questions. Will it really work? Why don't they just go with a traditional system? We'll try to bring you some of the answers, including a comparison to traditional systems, which are a lot closer related than you might initially think. Sponsored by Brilliant. Rockets are powerful, really powerful. Even the smallest ones can create lots of noise and energy that can damage not only their surroundings, but also themselves. Starship, being the largest and most powerful rocket ever created, is definitely not an exception to this rule. Its launch pad needs to be built to withstand the heat and pressure from the 33 Raptor engines on its first stage, super heavy. Usually launch pads use lots of water to deal with this intense acoustic and thermal energy from their rockets. These are normally called the launch pad water deluge systems. But with Starship there's an added requirement. The launch pad must also be ready to support another launch within hours to enable an incredibly high launch cadence. Starship is obviously not there yet, but Starbase is the proving ground to make this goal a reality. This is one of the many requirements that shape the decisions that led to the current design of Starship's launch pad. The new water-cooled steel flame deflector aims to precisely protect the underneath of the pad from the fury of the Raptors. This was something that was clearly needed if you saw what those Raptors did to the concrete pad during Starship's first flight. The pressure of the Raptor's exhaust essentially broke through and snuck under the concrete and into the sand underneath the launch pad, creating a crater. To solve this, SpaceX had to build a really strong foundation, something that wouldn't let the Raptors go through as easily. This basically prevents their exhaust from going through the ground and destroying it. But on top of that foundation, instead of flat concrete, they installed a giant steel plate that the Raptors would be firing against. This plate would not be eroded as easily as the concrete, reducing the chance for pressure to go into the ground. But even this was enhanced, so to speak, with water channels inside of it and holes that would let this water come out in some sort of cooling system. This is when this goes from just being a plate to what SpaceX calls a flame deflector system. In the words of Elon Musk, this system is like an upside-down shower head. The steel plate is filled with water at high pressure that is then released through holes. The water is then vaporized from the heat of the engines. By doing this, the vaporized water takes the heat away, which would have otherwise gone to the steel plate. This essentially makes the steel plate more robust and, more importantly, rapidly reusable. And this is the key takeaway. Without the water, the steel would most likely melt, and instead of raining pieces of concrete, we would have raining pieces of molten steel. I'm sure no van could take that. Although this water may also dampen some of the sound from the Raptor engines, its main purpose is not as a sound suppression system, but merely as a coolant for the steel plate. Now, there's more to the water than just cooling, but first, here's Sawyer with a word from our sponsor.
In 100 feet, spin in a circle. Wait a minute, I'm not doing that. Who coded this thing? Obviously someone who didn't use the sponsor of today's video, Brilliant.org. Brilliant has thousands of lessons related to math, science, and yes, even computer science. In fact, their lesson on thinking in code actually lets you code. From robots collecting coins in video games to, yes, helping your GPS find the best route, it gives you the simple tools to run your own code and figure out how these darn fangled computer things work. To get started with a 30-day free trial, visit brilliant.org/NASA spaceflight or click the link in the description below. The first 200 of you will get 20% off Brilliant's annual premium subscription. Now, if you'll excuse me, I need to find my way to the phone store to fix this GPS.
Okay, the water is mainly there for cooling, but how does it flow out of the plate? A usual question that we've seen from our audience is precisely about the flow of the water stream and in general why it comes out of the plate in the way that it does. You can see here in this video SpaceX shared on Twitter, it looks as if there's no water in the middle and all of the water is going outwards and through the legs of the orbital launch mount. Why doesn't that central point melt at all? After all, it doesn't seem like there's much water on it. Well, to understand how it works, we need to look at this system from another perspective. Super Heavy's 33 Raptor engines sit above the plate, and these are arranged in a central cluster of 3 engines, a middle ring of 10 engines and an outer ring of 20 engines. If we project these onto the plate, you can see that the 3 center engines are the only ones impinging right in the middle of the plate, where there's less water. The middle ring of 10 engines follows closely, but then the outer 20 engines are the ones facing the majority of the water on the outer portions of the plate. As you can see, the flow of water increases from the centre out precisely because the engine count on Super Heavy increases as you go out. That middle portion of the plate sees the least heat and pressure from the engines, so it's not a huge deal. The outward going pressure also helps carry the pressure and heat of the exhaust away from the OLM instead of keeping it all underneath the pad. I mean, think about it. Without the water, the exhaust of the engines already goes outward once it hits the ground, so why fight it? There's your quote for this video. Just go with the flow. Furthermore, you can see that the plate has a circle of water coming out of it for each of the outer 20 engines. This water is not only angled outwards, but it is further pushed out by the water coming from the centre of the plate. If you look closely, the plate even has its own holes with water coming out of them to protect the base of the legs of the orbital launch mount. As you can see, this system keeps all of the important bits cooled while the engines ignite. In order to achieve this feat, SpaceX had to put together not just a lot of concrete, rebar and the big water-cooled steel plate under the pad, but it also had to lay down a lot of pipes and bring in new water tanks and pressure tanks. After all, the water doesn't just pop out of nowhere. Some serious plumbing is involved. The flow of water begins in Brownsville. Here, tanker trucks take the water mainly from fire hydrants, but they may also take it from other municipal water storage tanks. These then travel down Highway 4 to the launch site. Here at the launch site, the trucks unload the water in these 6 large storage tanks for use on the flame deflector. Multiple sets of pressure tanks, which are generally called multiple element gas containers, hold the nitrogen used to push the water out to the pad. 2 main pipes channel the water and discharge it into 3 manifolds that then distribute it into the plate. One pipe, the one of smaller diameter, supplies one of the manifolds, while the other, larger diameter, supplies the remaining 2 via the use of a Y-shaped connector. The operation of this system is not simple. First, some water is flowed through the pipes all the way to the plate to clear out the air from the system before running it at full pressure. We've seen this happening multiple times before testing the system. It always looks as if there's some water trickling out from the plate. When the time comes to activate the system, full pressure is applied. A relief valve opens on each of the pipes leading to the plate to control the initial flow of water through the plate. Once at a steady state, the valves close and the water comes out at full pressure. At that point, everything is ready for the Raptors to fire. When it's time to shut the system down, a set of relief valves on the water tanks open and liberate all the pressure in the system, which creates a really loud noise. With the pressure gone, the water recedes and stops flowing through the plate. While some of the hardware here is new, such as the plate itself, a large majority of the hardware is reused from the old original Starship launch pad at Launch Complex 39A. In case you don't remember, this was going to be Starship's first orbital launch pad, back when all SpaceX was doing at Starbase was just some static fires of Starhopper. SpaceX reused the majority of the pressure tanks, the 4 smaller water tanks, most of the water pipes that lead to the plate, and even the manifolds for that plate. We actually made a video about it when it happened all the way back in January. By the way, whilst we've been working on this video, SpaceX has brought a 3rd large water tank, making it a total of 7 storage tanks at this water tank farm. However, as of writing, this tank has not yet been plugged in, and SpaceX may not do so until after the 2nd flight if they really are in a hurry to fly. With all of this covered, there's another question. Why do it in this way at all? Why does the plate need to have holes in it, and why is it pressurized in the first place? Couldn't the plate just be water cooled without throwing a bunch of water out? The problem, but also the saviour here, is the water vapour. Heating up water takes a lot of energy, but vaporizing it takes even more. All of this energy is essentially taken out of the exhaust of the Raptor engines and pushed away. But this could become a problem if the plate didn't have any holes in it. The internal pressure would build up and there'd be no way for it to escape, and you'd have a steam explosion inside of it. A water-cooled plate with holes in it, but without outwards pressure for the water, wouldn't fare well either. The water would still be trapped in the plate because the pressure of the Raptor's exhaust would not let it get out of the holes. While the water vapour has its problems, it also has the advantage of essentially creating a protection layer over the steel plate. You can see in this shot by Mary that instead of vapour, all you can see is a water cloud. That's good and expected. As the water leaves from underneath the pad, it cools down, condenses, and forms these white water clouds. You can see the great difference that the water system makes when it's present versus when it's not. During Booster 7's static fire test, the flames from the engines extended really far away, whereas for Booster 9's static fire test, they were too busy heating up the water to go any further away from the orbital launch mounts. In fact, you can kind of see how the water reacts to the different amounts of engines being ignited. It looks like during the very first second, only half of the engines are running, so most of the water comes out in the form of a cloud. And then, once the remaining engines start, it's as if there's so much heat going on that it all turns into pure transparent vapour. This is why water, and at pressure, does the trick. Sure, you could just put a big flat thick steel plate under the pad, no holes, no water, just a really thick steel plate with no cooling. It may survive and frankly, it works on smaller scales. The problem with this is that it would erode and weaken with every launch, and eventually you need to replace the plate after a few flights and do this process all over again. That doesn't sound to me like the kind of launch pad that can be rapidly reused. Imagine if a runway had to be entirely resurfaced every 6 takeoffs and landings. Commercial aviation just wouldn't be possible. Now, I'm sure a lot of you at this point might be thinking, why does this have to be so complicated? Come on, just build a flame trench, and I get it, it's easy to say that. It's how it's always been done. But SpaceX doesn't operate like that. Doing what has always been done isn't really their thing. Besides, when you look into it, building a flame trench really doesn't solve any of these problems, but rather just reshapes them. Normally a flame trench for the vehicle the size of Starship would need a pit somewhere around 20 to 30 meters deep, a flame diverter to divert the exhaust away, and a way to keep everything cooled in the path of that exhaust. That's pretty much how it is right now. The difference is that the exhaust is not channeled in one single direction, but rather is free to move in every direction, and the flame diverter, instead of being angled, is just a flat plate on the ground. You would still need a way to cool that flame diverter. If it wasn't water cooled, then you'd need at least a way to spray water on it so that it doesn't just melt and need to be changed every handful of flights. In fact, this is what SpaceX already does at their Falcon 9 launch pads with a water cooled steel flame diverter. Even the original Starship launch pad at 39A, which we mentioned earlier, was going to feature a giant water-cooled flame diverter 20 meters wide and 20 meters tall. But this was eventually removed from the design in favour of the current one. Whilst there's no definitive answer, one could probably say in hindsight that they went in this direction because with the current setup, SpaceX is able to roll 2 different platforms under the launch deck to either work on the Raptors or swap them out. Though not impossible, this would be much harder to do with a traditional flame diverter. So as you can see, this is not a simple system, and it is definitely a one-of-a-kind water deluge system. But you may wonder, why doesn't it act as a sound suppression system? The key to this is in what Elon mentioned a few months ago in a Twitter space. He precisely mentioned that Starship is so far away from the booster engines that the reflected pressure is not a big deal for the payloads, as by then the pressure is dampened by the air and the structure can take the shockwaves. And this doesn't make Starship the only super heavy rocket to not feature a sound suppression system. The Saturn V launch pad didn't have this at all, and rather used water to avoid everything from melting, just like the water deluge system at Starbase. Water was sprayed all over the Saturn V mobile launcher, down from the launch umbilical tower, as well to protect all of the gantry arms and other tower systems, and also down through the flame trench to protect the flame deflector, which still needed to be refurbished for every flight. It wasn't until the space shuttle flew when both Launch Complex 39A and 39B got their sound suppression systems and the now iconic water towers. This was needed for the shuttle for a variety of reasons, the main one being that the orbiter, where the crew and cargo resided, was much closer to the engines. The reflected pressure not only affected the airframe of the orbiter, but also its heat shield tiles. This was best demonstrated during the first flight of the space shuttle STS-1, when at SRB ignition, a bunch of tiles on the aft end of Columbia were thrown off and the body flap was bent out of position. This was due to a miscalculation in the amount of water needed for the sound suppression system, and the whole thing had to be upgraded for the next launch. So, as you can see, this pad is really not that different from traditional systems, and with everything put together, these decisions start making a lot more sense. But despite its similarities with past systems, it's certainly a new and cool way of not destroying the pad, and most importantly, being able to use it again without having to work on it for weeks, or even months. Forget about just one launch. Think about the end goal: multiple launches a day. Could anything like this even support this goal? What could be changed eventually to make this even possible? I'm sure you can agree that this is most likely what SpaceX engineers are thinking about next. You probably already know how design and engineering works in the company. In a nutshell, it consists of deleting systems that are not needed and optimizing those that are needed. So can this whole system be removed at all? Maybe, but the launch pad would probably need a major concept overhaul. For example, you could have the rocket sitting on a much higher launch mount, but then you'd introduce other issues such as reduced access to the vehicle, worse handling, etc. Let's assume that they have to stick with this system. What is it that could be optimized? Well, for one, they currently need to truck in all the water directly to the launch site, and that's not ideal, to say the least. You can't load propellant into the rocket for the next launch whilst also refilling the water storage tanks. It's also not easy to reuse the water from the previous launch because most of it vaporizes. SpaceX currently has a pond to recover some of the runoff water that does not vaporize, but this is still nowhere near capable of recovering even a quarter of all of the water used. A bunch of it essentially escapes the surroundings of the launch mount, either to the other side of the launch site or into the flats to the south and east of the mount. One way of recovering more of this water could be just extending this runoff water pond as far as they can whilst not disturbing launch pad operations. But this would then need a way to capture the water from this pond and treat it before putting it back in the storage tanks, something SpaceX currently doesn't have. That still doesn't solve the issue with having to refill the storage tanks at the launch site. This refilling would ideally not need people being that close to the rocket, so one potential solution could be laying down a pipeline to make larger storage tanks outside of the hazard area. This larger reservoir could then be constantly refilled without interrupting launch operations. But even this could still be further improved by just taking water from the Gulf and treating it via a desalination plant. This water could then not only be used at the launch site, but also perhaps for employees at the production site. This was in fact part of the operation SpaceX initially proposed to the FAA at Starbase, and that it decided to de-scope to accelerate the environmental approval of the site. After all, running such a facility not only alters the surrounding ecosystems, but also needs a lot of energy. This would mean the need for a power plant on site, which further impacts the environment, so on and so forth. I'm sure you can now see why SpaceX decided to ditch this all for the time being and concentrate on initial launch capability. What's clear is that this is just the beginning of this system. There's lots of room for improvement, and perhaps we may see some enhancements. We've talked about protecting the underneath of the launch mount, but what about the top of it? Could we be seeing in the future water also sprayed over the top to protect it from these launches? I don't know about you, but these are things I'm definitely looking forward to figuring out as Starship flies more and more. I wouldn't want to finish this video without stating the obvious. We still haven't seen this system in action for a launch. When Booster 7 performed its 33 engine static fire test, which became 31 engines, the concrete under the pad held up pretty much unscathed. The orbital launch mount legs ended up burnt and there was some small erosion, but at the end of the day, it didn't look as dramatic as it ended up on the day of launch. This was primarily because during the static fire test, the engines were running at 50% thrust, whereas for launch, they ramped up to 90% thrust during liftoff. The same applies to Booster 9. The flame deflector performed well during Booster 9's 2 static fire tests, but the true test is during launch. It is true though that for this next flight, the startup sequence will be different from Booster 7. Elon already had mentioned that for the first flight, the startup sequence of the Raptors was planned to be long, the idea being that this would be gentler on the engine startup sequence. For the next flight, however, this will not be the case. Based on what we've seen during the latest static fire test, the startup sequence should look more like this. At around T-7 seconds, the water-cooled steel flame deflector system is activated. This is evidenced by the opening of the relief valves on the supply pipes. 3 seconds later, at T-4 seconds, these valves close and the water reaches full pressure. At T-3 seconds, the engine startup sequence begins, and within less than 2 seconds, all engines should be up and running at 50% thrust. While this is not Super Heavy's full potential, this is still about 3,800 tons of thrust, more thrust than the Saturn V rocket. The engine should run at this level for about a second or so until the time comes to commit for a launch. This is when all engine parameters and systems are checked out and Starship's onboard computers have to decide whether to actually go ahead with the liftoff and ramp up the engines to flight power or abort and shut down the engines. Unlike Falcon 9, Starship's hold-down clamps open well before engine ignition, meaning that the rocket is just standing on the launch pad pedestals. This was at least the case for the first flight, and given the lack of any major change in the hardware and operations regarding this, it doesn't look like it'll be much different for the next flight of Starship. Under this circumstance, in order to lift off the OLM, all the rocket needs to do is just ramp up the thrust of the Raptors, and once the thrust is higher than the weight of the vehicle, it will start moving up. This should occur once the Raptors pass the 66% throttle mark. Now, we don't really know what will be the throttle level of the Raptors for the second flight of Starship, but if you imagine the rocket already lifting off when these cross the 66% throttle, then that means they don't reach flight power until after Starship is off the mount. In any case, this whole shortened startup sequence could definitely help improve the chances that the system does work during the next launch. So the question now goes from us to you. Do you hope it'll work? Do you think it'll work, or will we see another crater under the launch pad? Let us know all your thoughts down in the comments below. Thanks to Brilliant for sponsoring this video. Be sure to get your 30-day free trial and get 20% off their annual premium subscription using the link in the description. Thanks for watching, and goodbye.